Hi, welcome to the Signal Pad. I have a really cool episode for you guys today. We'll be taking a look at the Keysight EXA Signal Analyzer / Spectrum Analyzer, and I'm going to do a very extensive review of this unit, including a teardown, operation, as well as a whole bunch of different applications that's built into it. Now this is a very long video. It's over 1.5 hours long, so there are pointers in the description that allow you to jump into a specific section of the video. But I hope that you get to watch all of it because they're all related in a way, and then you can pick up a lot of useful information. Now of course I can't cover everything with an instrument like this. It's going to take quite some time to go through all that detail. But nonetheless, let's go ahead, take a look at what's going on. I hope you enjoy the video. So how does the Keysight model overview look like for the X-Series Spectrum Analyzer? Well, here I have it right over here. The X-Series Spectrum and Signal Analyzers vary from the CXA, EXA, MXA, PXA, and finally the UXA model. And of course, as you go up in model, you're going to have quite a bit of difference in performance. Now the EXA, which we're going to take a look at today, has a unique position. It's because even though it's the second model here, it still has millimeter wave capability, so it can still be configured to operate all the way up to 44 gigahertz. And that is not true, for instance, for the MXA, and certainly is not available for the UXA yet. And the PXA remains the instrument with the highest frequency of operation of 50 gigahertz. Now if you look at the UXA, which I've used before, and it is a fantastic instrument. It has a brand new GUI, brand new touchscreen interface, and it runs multiple applications in parallel. It's just a totally different paradigm and a way of using the spectrum analyzers. And this is undoubtedly a reaction to the fact that Rohde & Schwarz has had spectrum analyzers with advanced GUIs for quite some time now, and Rohde & Schwarz is definitely Keysight's biggest competitor in this area. The highest frequency of operation of the PXA at 50 gigahertz is still short of what Rohde & Schwarz offers, which now they have all the way up to 85 gigahertz. But of course, that's a very niche market. So whether or not Keysight thinks that that's a market that is important to them remains to be seen. But nonetheless, now if you look at the performance of the EXA, as we go up, we are looking at a phase noise of minus 106 dBc per hertz at a 10 kilohertz offset at 1 gigahertz, which is, reasonable, it's respectable, but it's not intended for state-of-the-art PLL measurements. And if you go all the way up to the UXA, there is an enormous improvement. We're talking about 30 dB of improvement in phase noise, which is huge. Nonetheless, the EXA being able to do millimeter wave capability, and at the price point that it has, it puts it in a very attractive position for a general purpose spectrum analyzer. Now, obviously, you can go up to 1.1 terahertz if you have external mixers, but unfortunately, the external mixer capability is only available for instruments that are operating at 32 or 44 gigahertz. They don't have mixer capability for 26.5 gigahertz models or below. Even though the PXA certainly does offer that at 26.5 gigahertz, you can still have external mixer capability. And in terms of the noise floor, you can see definitely some improvement from the EXA going up as well. And the list of applications that the EXA supports is just huge. I mean, I have all these applications installed currently on the model that I have here, and there is everything under the sun, every single ISM band, every type of different wireless application standards with all the required tests and masks and everything is already included in different application that it supports. Now in terms of real-time spectrum analysis, the real-time spectrum analyzer options only start from MXA and going above, so the EXA does not support that, but it does support 40 megahertz of instantaneous analysis bandwidth, which means that you can do baseband demodulation and all those things, and we will take a look at that as well. And the other point to mention is that the linearity of the EXA at 18 dBm for a TOI is also fairly respectable. Of course, it improves significantly going up to the UXA. Nonetheless, now that we have a fairly good idea of where this sits in the lineup and what the purpose of this instrument is, so you can have a better idea of whether this would meet your needs. So let's go ahead and take a look and see how this instrument actually operates.
We're going to take a look at the EXA signal analyzer from Keysight, and we're going to take a look at the architecture, the building block, and we're going to do a teardown of the instrument. Once I told Keysight that I wanted to do a teardown of the EXA, they went ahead and they sent me all of this, which are all the different LO building blocks, the RF circuits, the baseband processors, all the different boards that go into making the EXA signal analyzer. This is fantastic, and I really appreciate this, not just because it's a lot of effort to put a package together and send it to me, but also because it represents a level of commitment from Keysight's perspective toward their potential buyers and existing users. After all, you really won't need to understand how the instrument is manufactured, how it works, what the principle of operation is, before you can make an informed decision, and also because that's the only way to get the best out of your measurements. And Keysight and HP and Agilent, they've always been really good with that. So I really appreciate it. Big thumbs up from me for sending this to me and being able to show it to everybody, and being so open about it and actually sharing all this valuable information. A lot of learning experience and very useful, definitely for the people who are going to be using it. So we're going to go look at the block diagram first, and then depending on the different sections, we're going to come back to these boards and look at the boards and then compare with the block diagram, and that should be a very interesting section to understand the instrument's operation. So here we have the block diagram of the millimeter wave EXA from Keysight. Now this is the millimeter wave instrument, meaning that this is the model that operates above 30 gigahertz. In fact, you can buy these all the way up to 44 gigahertz, as I showed while we were doing some model comparison. Now, as is with any spectrum analyzer operating on such a broad range of frequencies, not all the conversion is done by a single mixer. As a result, the signal path takes different routes throughout the instrument depending on the ranges of frequency that's being looked at. And this is broken up into different pages in the service manual, and here right now we're looking at the section that operates below 3.6 gigahertz. Now the service manual is 657 pages, so we're not going to look at everything obviously, but I want to give you a good idea about how the instrument operates so you learn how to get the best out of your measurements. So let me get rid of this up here so we can get a slightly larger view here. So let's start from the beginning. This is the RF input. This is where all the frequencies from 9 kilohertz to 44 gigahertz enter the instrument. And the very first thing they see is this small attenuator, which is a 2 dB, 2 dB, 6 dB, broken up into 3 sections. And this is where the CAL signal, which is used for alignments and so on, enters the instrument itself. So this front end switch will switch into the CAL position in order for the instrument to do internal alignments and so on. After that, we're going to go into another set of attenuators. These are almost binary weighted, 10 dB, 20, and 30, and of course the combination of these two gives you a whole range of different mechanical and electrical attenuation ranges. So, and the signal after that enters this low band switch, and this low band switch is responsible for routing the signals that are below 3.6 gigahertz to a different path. And you can see some input protection over here, and once it's broken down here, all this upper section is not connected to anything anymore. And the signal goes through a low pass 4 gigahertz filter, and that makes sense because you don't want this portion of the circuit to process anything above 3.6 gigahertz. So they cut everything out to make sure they don't have any extra harmonics. And then you have an option of going either to an electronic attenuator, which we'll take a look at once I'm looking at the instrument, or if you have the option of a preamp, it will go through the preamp. And the preamp here will give you another 20 dB of gain, lowering the noise figure of the front end significantly, bringing your noise floor down. This will be very useful when making noise figure measurements, as we will do. Then the signal is processed by a mixer. Now, normally spectrum analyzers, which go all the way to these higher frequencies, don't like to process signals at very low frequencies. They want to bring it up to a kind of a mid-range of frequencies before they get processed, and this is in fact what this mixer does. This mixer actually up-converts the signal all the way up to 5.1 gigahertz, and the output of it is amplified and sent out through an external filter because they want to use a nice high-quality factor, high-Q microwave cavity filter to really band pass that signal to make sure that it doesn't have any other components that they don't want. And obviously the LO distribution network here is responsible for tracking the desired RF frequency so that the output of the mixer is kept exactly at the center of 5.1 gigahertz with 150 megahertz of bandwidth and so on. Then that is IF out, called the IF out here, is fed back into the instrument, and now that signal is sitting at 5.1 gig, and it can actually be processed by one of the 3 main subharmonic mixers. And this mixer over here can process signals from 3.6 all the way to 17.1 gigahertz. So there is a solid state switch here that then gets switched into this direction, and the signal would then enter this mixer. And this mixer receives its LO again coming from the outside, and this LO takes this path over here going to a balance, becoming differential and amplified. So this is actually a balanced mixer at the LO port, and is most likely also a subharmonic mixer all the way up to 17.1 gig, and in fact I'm pretty sure that it is. And you have then the signal coming out. Now this is an IF signal centered at 300 at 22.5 megahertz, and that signal is then sent into the front end controller, and I will talk about that separately. So you can clearly see that the signal path, no pun intended, of the RF signal coming all the way through here, below 3.6 here, getting filtered, getting up converted to 5.1, going through an external cavity filter, going back over here, getting mixed down all the way to 322.5 megahertz. Now if we go ahead to check another signal path, let's jump up to 3.6 to 17.1 gigahertz. Now this portion of the circuit is no longer needed, and you can see that we go through the same front-end mechanical attenuators as to be expected. So these are 44 gigahertz rated attenuators, and then we switch up into this path which processes everything from 3.6 all the way to 44 gigahertz. And if you have the preamp option, you get a 30 dB boost of signal power over here for these frequency ranges. Once again, very helpful for doing a low noise, low signal power measurement, so that your signal is not buried in the noise floor of the instrument itself. This will significantly lower the noise figure of these mixers. The signal is then sent out over here. Let's ignore this for a second. It's going to go through the YTF. The YTF is the Yig tuned filter. Of course, this is a high quality narrowband Yig tuned filter which tracks the RF frequency, and this is absolutely necessary for these subharmonic mixers. If you don't have this, then your broadband signal covering, you know, from 3.6 to 44 gigahertz is going to just overwhelm these mixers with tones and harmonics and images and everything, and it's going to be unusable. So this is absolutely necessary, and that is going to be tracked and following the LO and the RF signal. Now these things are aligned, of course, because as the temperature changes and the age and so on, the alignment gets shifted around. So that's why this internal alignment circuitry exists. So one of the reasons is to tune and align the Yig tuned filter here. So the output of that is now a narrowband signal, and that signal then goes through this other mixer. It gets amplified. There is a three-way switch here, which is, these are all solid state switches, and that goes in through this same mixer here. A separate path is chosen and then goes back out again. And the LO path is slightly different. You can see that the signal here, they double the signal first, and they go through a 14 gigahertz low pass filter to get rid of the harmonics of the LO, and then again becoming a balanced differential and so on, the same as before. The IF lands once again to the same frequency at 322.5 megahertz, which is exactly what you want. All of these mixers will always down convert the signal, no matter where it is, into the same IF frequency. Now if you jump up again to 17.1 to 34.5, everything remains the same, except that we're going to be using this top mixer over here, and again it's driven with differential LO, and the same path is chosen in order to do that. We're doing exactly the same thing, except this mixer is running on a different harmonic of the LO, and therefore it's going to land back the same ranges of frequencies, just a multiple higher, back onto the same IF. Now we go again forward from 34.5 to 44 gigahertz. Now this is purely in the millimeter wave region. Everything is the same again, except the path is now single-ended. So in fact, they're doing a single-ended LO drive for this final subharmonic mixer, probably because they can't process the signal, the LO differentially, and then have the subharmonic mixer working differentially. It's probably a single-ended device, not fully balanced, because this frequency is very high here. So it's to be expected. And then they have the same IF. Although I'm a little bit surprised that this path is never used, I suspect that this is an error in some way, that this should be going down through here, but you can see that between these two versions it's actually not. So I suspect that's probably a mistake, or maybe not, but otherwise then they're never using this, which doesn't quite make sense. Anyway, so then the IF coming out over here goes through this front-end controller. This front-end controller has all the digital signal processing required to control all the attenuators and the Yig filter and so on, so everything's taken care of through here. This is the main path of the IF, which this main IF then gets digitized by the baseband section of the circuit. But there is also another path which you can take, and there's actually two other paths. The other path down here, which has its own mixer and its own VCO here, can be taken out of an auxiliary IF at the back of the instrument. And this is really, really helpful, because the analysis window of these instruments can only go up to 40 megahertz for the EXA series, as I mentioned before. So if you want to look at a wider IF simultaneously and digitize it, if you have the auxiliary IF out option, that's exactly what you can do with that. You have a much larger signal, over 100 megahertz, which you can take a look, and hopefully we can do some of that experiment here with the EXA we have. Then you also have this other option here that the signal can be switched to this path, and once it's switched to this path, this is the 40 megahertz analysis window, which is going to go through a different A to D converter than this one. They don't need to be digitized the same way. This is the regular view, and this is the baseband view, the 40 megahertz analysis window view, so which is fantastic. We'll take a look at that.
So let's go ahead and follow the IF signal here, and if I follow it, I will get into this block diagram, which is a 25 megahertz system block diagram. Now we don't want that because we want to take a look at the 40 megahertz version. That 40 megahertz is the upgrade, and of course the unit that I have here in the lab is fully loaded. It's going to have the 40 megahertz analysis one. So let's jump to that one. This is basically the same thing, except it has much more processing power and a 40 megahertz bandwidth. Let's take a look at that then. And we have the IF coming in at 322.5 megahertz, and this is the IF coming from the previous section. And then it enters an analog IF section, and this is purely an analog portion of the IF, has no data converters in it yet. And this includes things like the comb calibration, which is used to switch into the path to get the calibrations for the IF and so on. But it also has the very important down convert mixer, which mixes the 322.5 megahertz signal all the way to 22.5 megahertz. Now this is within the window of the frequencies that our high resolution ADC can actually now process. And after that, there are different filters and so on depending on the IF configuration that you've chosen, and there's also the burst carrier trigger used for some of the options in the instrument to detect some carriers that come and go at certain rates and so on. We'll probably get into that later when we're using the instrument. But then the output of that now sits at 22.5 megahertz. Once it comes out of that, then we have the entire digital IF section, and this is one of the other modules that I have. So we're going to take a look at it, and it's a really beautiful portion of the instrument as well. So we're going to take a look at this. So what happens with the 22.5 megahertz signal? Well, that has to be digitized now. This is low frequency, and all the everything that was processed from 9 kilohertz to 44 gigahertz ends up in here as the LO and the RF sweep the instrument, and that goes into a signal into differential converter there for the ADC input. Is a low pass filter, anti-aliasing most likely, and then it goes into a 16-bit A to D, and there is also some dithering added into here, and of course dithering is added to the ADC input to decorrelate any signal with the frequency, clock frequency of the ADC, and reduce spurious-free dynamic range, and improve the spurious-free dynamic range of the ADC. And that's dithering is a very common technique used, and of course they're going to implement that here. So then the output of the ADC goes into a whole bunch of digital signal processing section, which is responsible for everything, including all the fancy functionality of the 40 megahertz analysis, and we will get to that in detail, and I'll tell you some of the things it can do while we're looking at the board itself. Now the other path that we have is the main path that actually does the 40 megahertz digitization, and that path is a different path because they don't do 40 megahertz analysis on a 16-bit ADC, they do it on a 12-bit ADC, and that's this signal over here, and that signal then comes over here, and that is going to go all the way through here, and that's already down converted once again with another mixer that was in the RF section. Now it's sitting at 250 megahertz, and that goes through a whole bunch of different things, filters and so on, again some dithering added over there, and then it goes into this ADC. So depending on how you're using the instrument, if you're just using it for basic signal viewing, you will be using this path, and if you're using the DSP digital signal processing of the 40 megahertz bandwidth, you're going to be using this path, and I'm sure that there are some combination of both of them that are used perhaps. And then we also have the 100 megahertz reference clock that's generated from somewhere else going into here and getting doubled and split, and so on, and goes into the ADC clock when the ADC requires twice the frequency of 100 megahertz. All the different sampling frequencies of the ADCs are all handled over here, and a whole bunch of other digital portion here which controls everything under the sun for all of these fancy digital functions to be taken care of. All of them are handled through the digital IF. So what are all these LOs coming from? Well, the LOs are going to come from the reference and the synthesizer block diagram here, which is going to describe exactly how all the different LOs are generated. Now I have this board here we can take a look at. Unfortunately, I don't have this board. It would have been perhaps more interesting to take a look at this one because this is the main reference portion, and it has all the different PLLs already in here. There's only one PLL in here. But let's start from here. We have our 10 megahertz reference coming in here, or the 10 megahertz voltage control oscillator that's built into this board there, and that 10 megahertz reference is the foundation for locking all the PLLs. And you can see a whole bunch of different PLLs. Here's the 100 megahertz PLL. This PLL is locked again to this 10 megahertz reference. It's got triplers on it, it's got divider by 2 on it, it's got a whole bunch of different things generating just an enormous number of different LO signals distributed all over the place. All the instrument LO signals required for the mixers, the ADCs, the alignment signal, everything has to come from somewhere, and they're all generated over here. And the high frequency portion of the PLL is then taken off out of the 100 megahertz, going through a doubler, a quadrupler, another doubler, all reaching all the way to 4.8 gigahertz, which will be the reference used for this DRO, the dielectric resonator oscillator here, which is a very high quality factor oscillator, and this 4.8 gigahertz oscillator is going to determine the main phase noise of the system, because this is the main LO used for all the mixers, and that then goes out over here, goes into a fractional N synthesizer with a VCO over here used as a reference for it, and then that is doubled and goes through a whole bunch of different filters and more doublers and filters in order to be able to get a very good isolated tone of the final LO that's going to be fed back over here into the instrument's front end for all the different mixers, subharmonic mixers, and so on. So this entire section over here handles all of the LO distribution, multiplication, and so on, and this is one of the key blocks that enables low phase noise from the EXA. Of course, the phase noise of the EXA is not as good as the UXA. That's going to be much fancier there, but nonetheless we're going to have a fairly good phase noise from this instrument as a result of this. Anyway, so I've talked a lot about the block diagrams. I hope that you found it interesting, and it's very cool to see how this instrument is made. So let's go back, and I'm going to show you this board over here, the RF front end. We're going to take a quick look at that. I'm also going to show you this board over here, which is a digital IF, as well as the LO synthesizer board, and that's going to complete this section, which includes the teardown as well, and then we'll get to play with the instrument.
So let's go ahead and take a look at some of these boards that I have. The first board is going to be the RF front end, and here's a block diagram of it just to remind ourselves. And the RF front end is the portion of the circuit that processes all the millimeter wave components, so it should be pretty interesting to take a look at it. And here I have it right over here. And what we expect to find is our triple mixers, our LO distribution networks, our front-end solid-state switches, and the different mixers that are there. Now, I've taken all the screws from the RF shield, and these RF shields also act as heat sinks. And if I were to go ahead and lift that, you can see that by the presence of these thermal pads that are going to be able to dissipate the heat. And the other side also has another board which has fins on it, which is another indication, and there's some isolated compartments there for EM shielding. And there is our board, and it's all covered up. We can't see anything, and there's a few reasons for that. One reason is because they obviously want to protect those circuits, probably for intellectual property, and also just to protect them and shield them really well. Now, by the height of these little sections, you can see how shallow they are. I suspect that they probably don't have a lot of packages under there, and a lot of die on PCB or a wire bonded or flip chip directly embedded. And all of the ASICs that are in here are going to be custom, either made by indium phosphide foundry from Keysight or some other gas foundry that they have access to. And now, looking at this, one of the other things you immediately notice is this cavity filter over here, and that filter is indeed the external filter that we were talking about before, required to have very high quality factor, and indeed they're using an external filter there, and that's to be expected as well, connected through these rigid SMA cables to the board. So the input is going to be right over here, and we know that because this is our highest frequency connector. Indeed, this is a 1.8mm connector, which easily goes to 44 gigahertz. No problem there at all. And you can see that the front end chassis here is different. It's most likely to support the connector, so they enter with a much nicer connector, a very solid build over here, as to be expected. They don't skim out on these high frequency millimeter wave stuff at all. And one of the other interesting things is that these little circles that you see there, there's tiny little holes underneath that, and those holes are necessary because when you reflow the board, the gas needs to be able to escape, because they probably put all these together and then they reflow it, and then they stuck these copper tapes on top, which seals them completely, and they have actually some special glue underneath them, and the sealing is necessary because most likely the ASICs aren't all in silicon. Like I said, they're indium phosphide or gas, and that means that they need to be hermetically sealed, which is very important. But nonetheless, even though we can't see them, we can follow the signal path. Here comes the RF signal. In between these two blocks over here is going to be our solid state switches, which is a three-way switch, goes all the way up to 44 gigahertz, and our triple mixer is going to be all embedded in here, which means that our IF at 322.5 megahertz is generated within this section. And it needs to be amplified, and I suspect that's what this little guy is. There's a little amplifier over there, and it has two balance at the input and the output, single into differential conversion with the center tap common mode there, and that's because the IC is probably differential. Interesting that they've gone through that route to go differential and back to single-ended again. And that's going to be the IF output. So where is the solid-state switch that selects which output the mixer is taken? Well, if I flip it on the other side, we can indeed see that we have a Hittite or an Analog Devices gas three-way switch over here, solid state switch, and this is probably the circuit that's responsible for selecting which IF comes out of which mixer. Now, everything else such as LO distribution networks, which goes to the triple mixer as opposed, and also for the low band path, are all going to be embedded in here. Now, we also have another mixer, as I talked about, the mixer that actually upconverts the low band signal to around 5.1 gigahertz, and that mixer, I think, is actually exposed. So we should be able to take a closer look at it, and I believe that's right over here. And there are some indications that that's the case, and you can see that you have like a few different paths of signal. This is where I believe where the the LO comes in, and you can see the LO come in here, goes into this little lumped capacitive there. We have some coupled line filters over here. We have a little transmission line with a stop, and then we have a different width of a transmission line, so they're doing some impedance transformation between these two, creating a reactive component in the junction there. And then they have some other capacitor components there, two little actual discrete capacitors, another transmission line over there connected to a bow tie stop. Following that, we can go over here. You can see that this is most likely our mixing element here. And we have another impedance transformer line where we have a signal coming from above here, which is probably going to be a RF, IF signal coming in. We have another stop to a nice discrete capacitor to ground, making a good stop at the end there, short there. And then we have the output of it coming all the way out over there. And that goes onto our cavity filter, exactly what the schematic says, or the block diagram says. You can see the mixer that has to go through the cavity filter. So it matches really nicely, and I think that's probably what's going on. And if I were to flip that to the other side, the location of these places where the solder mask is missing is a good indication of where those ASICs are, because they have removed the solder mask so they can make a better connection, better thermal connection with lower resistance onto the thermal pads on the other side. So everything works out quite nicely. All the other different LO ports and so on are all, of course, embedded under. And if you look closely, someone also has left a message. Oh, it's upside down. There you go. Actually, it's on the other side. I apologize. Here we go. And you can see it says P3 Love. Someone has used the ground stitching on this board to make a little symbol, which is kind of interesting because normally people just use traces, and this individual has used the stubs, which is kind of unique. And of course, people do this all the time. I have left a lot of drawings on different ASICs that I have made, because somebody made one. They look at it under the microscope. It's kind of a fun thing to do, and it's nice to see that someone's done that. And other than that, it's really otherwise pretty straightforward. All of our LO distribution paths are all embedded in there, and I don't think there's anything else that we can actually see. Unfortunately, I can't open these to show you because these are permanently connected, but I thought it's a pretty close look. It's pretty neat, and I wanted to point out the quality of the work that goes into this. Obviously going to be first class, as we shall see from the performance of the EXA when we use it. And Keysight, some of the best in the world, they really know what they're doing. So let's move on to a different board. So here we have the baseband digital processor board, and this is where all the magic at the 40 megahertz capture happens. This is again for the 40 megahertz version, not for the 10 or 25. So this is an upgrade that I have over here. And one of the very first thing to note is I've taken one of the heat sinks off, and you can see two big Vertex 4 Xilinx FPGAs here. And these FPGAs are critical because they provide hardware accelerated analysis within the 40 megahertz window. They interface directly to the A to D converters, which we will take a look at, and this allows you to do very fast power detection, spurious tone detection, and do things that you normally wouldn't be able to do if you were doing a sweep analysis. This is critical if you want to be able to detect intermittent events, which are not very common. It also has a deep memory of 2 GB, which is stored on the other side of the board, and we'll take a look at it when I flip it over. But without these hardware accelerated FPGAs, you wouldn't be able to do the fancy detection of problems that you normally would want to do on a 40 megahertz analysis. And to add on top of that, the VSA software, the Vector Signal Analyzer, runs natively on the Spectrum Analyzer because it runs Windows 7. But the nice thing is that the VSA has a direct hardware connection to this board, so it runs ridiculously fast. It can grab data directly from the hardware processed by the FPGAs and then just display it on the VSA. The processor doesn't have to do anything. The main processor of the PC, of course. You don't want that to be reliable, to be responsible for doing this type of analysis. You want it hardware accelerated, and they've done that here with these two big FPGAs. And the other things you can notice is there's obviously other FPGAs which are used for other little purposes, and this is the back of the instrument with all the different I/O interfaces. Notably, this connector over here is for the smart noise source, the SNS noise sources, and I have one of those, and we'll take a look at it and use it in one of our experiments. And the drive voltage for that and the interface for that is built directly on this board as well, and there's some expansion slots. I've also gone ahead and taken screws off over here as well, and underneath it you would find exactly what you would expect. All the clock distribution that you would need for this board are all over here. This board also has built into it a whole bunch of other interfaces that it has to take care of because it talks to many other components which are outside of this board. All of that needs to be taken care of as well, and the processing of course done on the FPGAs. And there's clock distributions and so on which will be embedded in here. And the ADCs are right over here, as I mentioned before, a 12-bit and a 16-bit. Just to remind ourselves, this is the block diagram. So we're looking for this ADC, and this clock distribution which has multipliers and filters on it, and of course all the DSP processing which was over here, which I just talked about. So we should be able to find those. And in fact, a very quick search reveals exactly where they are. And we have two ADCs over here. The first one is an Analog Devices one, and the second one is a Texas Instrument one. So let's start with this one. This is a the AD5527. And that's, as I said, the Texas Instrument part. This is a 12-bit, 210 megasamples per second ADC, and it has a DDR output, which is very helpful because you can interface with it really, really fast, and that's what you want, to be able to grab data from the A to D converter really quickly. This is the ADC that's used for the 40 megahertz analysis window. And its performance is quite good. It has about 70 dB of full-scale SNR with a 70 megahertz input. So that's exactly what you would want to use. The second one is an Analog Devices. It's an AD9446. This is a 16-bit A to D converter. Can be sampled up to about 100 megasamples per second. At around a 30 megahertz input, it has over 83 dB full-scale of SNR, which is perfect because the IF coming in is at 22.5 megahertz. So everything else is pretty straightforward. We have our multiplier path, which has a quadrupler. I'm sorry, it has only a doubler on it, and a whole bunch of different filters. All the filters are implemented in discrete lumped LC elements here because you can afford it. The frequencies are low enough, you don't need to have them embedded into the PCB. And we have some other paths again for LO distribution for the ADCs as well. And if I were to flip it on the other side, you can see a whole bunch of other components there. This is where our IF circuits, IF signals and the LO signals for the ADCs all come in, and I mentioned that those are generated by the LO synthesizer itself, and we'll take a look at that board next. Here's the back of the FPGAs, and here's our memory that you can see, just standard DDR memory it looks like, and everything else is just power distribution, DC-DC converters. These two transistors over here, which I'm pretty sure are responsible for the 28-volt drive voltage for the SNS noise source. And I'm going to flip it back over here again just to notice a couple of other nice designs there. You can see that the FPGAs and the digital section is completely isolated. There's a gap in here which completely separates the ground and the VDD and everything of this section for isolation from noise and switching. And all the signals from the A to D are two differential transformers coupled across magnetically, essentially. So there is no direct connection, which is great. Again, these people are, some of the best in the world. They know exactly what they're doing, and this design looks pretty nice and neat to me. I'm not sure how much more I want to talk about it. It's just the architecture is fairly clear, and it looks beautiful. Let's take a look at one other thing. That would be the end of the teardown. And here's the last board that I wanted to look at. This is our LO synthesizer board, so we expect to see a whole bunch of different sections of microwave filters and so on, as well as solid-state selectors and VCOs and so on. So let's go ahead and lift this guy up. I've taken a whole bunch of screws out of here, and take a look at it. It looks very nice, as to be expected, just like any other of the board that we were looking at. Let's just remind ourselves of the components that go in here. So we're looking for things like VCOs, fractional controllers, doublers, amplifiers, solid-state selectors, bank of filters, and again doublers and so on. This entire chain should be pretty obvious and detectable. So let's go over here and look for our VCO. Do you see it? Can you see it yet? It should look different than anything else on the board, and in fact, indeed, it's right over here. There it is. You can see it's very nice looking. It's got the RF transistor right in the center. Here's our VCO tank and above and below it, and you can see that inductors are embedded directly onto the PCB right there with what appears to be diode varactors there and the control voltage coming in. The output of that VCO is taken out over here, amplified, and if I zoom back out there, you can see we can follow the signal path very nicely from there. You can see the amplified output goes over here, goes through some filtering there, and then it goes through a BAL and becomes differential into a doubler. But this is at least what appears that is going on over there, and the output of the double signal then comes out and goes through our selector there. This is a solid state switch again. Now another interesting thing to note is that I don't see any of the filters embedded on the PCB top layer there, and they're not at the bottom layer neither. But because of the ground stitching and because of the fact that there are these shapes in the ground stitching, it gives me the impression that those elements of the filters are embedded in the intermediate layers of the board. And that's really interesting. I wonder why they've done that. Perhaps to protect how they were made. But you know, I guess you could X-ray them and really find out. But they're not at the top or the bottom. And this is interesting because if you're going to embed them in the intermediate layer, that limits you in your stack up, because now you have ground above you and ground below you, and that could mean that it's going to put some strain on the lithography of the board in order for your components now to fit your new stack up, which is okay. I imagine that they know exactly what they're doing, but at least that's what I think is going on, that they're all embedded in the intermediate layers. Now everything else, all the selectors between the filter banks are all solid state, and they're all these little Hittite components that you see all around here. And the signal coming in, and you can see these are all the three-way switches, and then going into over here, and then going through the filters, and here's a doubler here from Mini Circuits, here's another doubler there from Mini Circuits. So the signal is selected between which path you want it to go through, which filter path, which are these ground teaching reveals them, and then selected again, and then goes to doubler again, select which filter path, and doubled again. So the overall signal, we have a reference coming in, which is from the dielectric resonant oscillator. This is our clean reference 4.8 gigahertz coming in over here, goes through here, then it goes through some amplification. Over here again becomes some more amplified or differentially to single mode converted, and then goes over here. In this appears to me to be the fraction element controller. The output of that then goes over here and controls the VCO. So, and the output of the VCO then goes over here, gets doubled and so on, doubled and filtered, and comes out of here. So the signal path is very nicely visible through the PLL. It's very nice and clean, and you can see the FPGA Spartan 6 over there in the middle, a whole bunch of DC-DC converter sections scattered all over the place, all of them individual compartments of signals so that they don't contribute to noise from each other, and they put the VCO in the corner as they should. And if I were to flip it upside down, you can see exactly the same thing at the back. You can see all the ground stitching openings for what I believe where the filters are. And everything else looks pretty good. I didn't see any of the filters under, that's why I'm guessing that that's where they are. And I mean, these shapes are pretty revealing, at least to my eyes. The interesting thing is that there is another chip that appears to be another fraction element controller, which is kind of unusual, sitting over here. I'm not sure why that is there. It doesn't show up in the datasheet, but it may be that simplified, or that, you know, we're making some assumptions on this board anyway. But other than that, looks fantastic, and pretty happy with it. Again, great A quality as to be expected from Keysight, and especially from such an expensive instrument. So it looks wonderful. There you go. This was a pretty extensive teardown of the few boards that we had. Luckily, they only sent me 3. Otherwise, this portion would have been 4 hours long. But don't worry, we got lots of cool experiments. I hope you stick around to watch, and let's go get to our fancy experiments. Alright, and this was a close look at the block diagram and the teardown of a couple of the important modules. Luckily, they only sent me 3 modules, otherwise this teardown would have taken 2 hours on its own. But now that we have a good idea of how the instrument operates internally, and we've taken a look at some of the critical blocks, we can now go and do some experiments with it. So let's move on to the next section. And here we have the front panel of the EXA signal analyzer by Keysight, and it has a very recognizable spectrum analyzer look to it. If you've ever used any of the Agilent or even the HP spectrum analyzers, you're going to feel right at home, because the button configuration and the GUI configuration is very consistent and has been refined over time to be able to give you the quick access to everything you need. Now, the biggest part of the front panel is obviously occupied by the LCD screen. This is a very sharp, very crisp, really bright LCD screen. Now, it doesn't have a touch screen. As a result, the instrument relies on you to use the keypads and the buttons that are in the front very heavily, so the instrument is designed for interaction with the buttons, which I kind of enjoy. Now, on top of that, we have on the right side the power probe connector, which is a mandatory connection there. You have the headphone for the audio demodulation. You have 2 USB ports, and at the very bottom of that, you have, of course, the RF input. Now, on a 26.5 gigahertz spectrum analyzer like this one, this is going to be a Type N connector, and here I've put the Type N to K connector converter there so that we can be SMA compatible and be able to switch things in and out very quickly. You also have these bunch of buttons up here, which are your analyzer setup. This is going to be the frequency, the vertical amplitude, the detector type, the source control, resolution, bandwidth. All the main controls of the spectrum analyzer configuration are right over here. This is what you're going to be interacting with the most. At the bottom of that, you have the measurement section. Now, for depending on what application is loaded, the measurement, the mode, and the setup of that is going to give you all the necessary settings and configuration for that application. And this has been kept consistent no matter what you load. So phase noise, noise figure, or any of the other types of wireless standards that you load, you're always going to be able to configure and find what you're looking for with this. And they've done a really good job of keeping that consistency so that you never get lost in the hundreds of menus that are available.
On the right side of that, you're going to have your marker, which we're going to talk about later, and then the utility buttons, which, you know, system configuration, loading files, saving files, and so on, are going to be handled there. The trigger, restarting and doing a single or continuous measurements are here. All the entry button keypads over here with the directional pads right above it. The rotation knob here, of course, also available, and a few other buttons which aren't used as often. Some of the applications still take advantage of them. All the soft buttons on the side of the screen are, of course, going to be there, which is going to be depending on what is displayed on the screen. Your window management, maximizing, minimizing, and swapping windows, the volume control for the built-in speaker, and the help button, which can be very handy. Other than that, it's really straightforward. And the top right is where we would have had the external mixing capability. Unfortunately, as I mentioned, the 26.5 gig version of this instrument does not support that. Only the millimeter wave does. And that's unfortunate because you should be able to, in theory, use it. And perhaps there's an LO configuration that doesn't allow it, but I don't see why they have omitted that. On this panel over here, which is empty, normally on the higher end spectrum analyzers like the PXA, you're going to be able to have your baseband inputs directly here, so you can actually feed IQ inputs into the baseband analyzer, which this instrument also does not support. None of the models of the EXA support that, but if you jump up to the higher models, you will be able to add that to that instrument. Let's go ahead and take a look at the back of the unit. In the very center, of course, we have the main motherboard, which houses the CPU as well as the Windows operating system. And you can see some typical interfaces from that Windows machine. We have GPIB and LAN, we have VGA. There is no DVI port yet because these type of motherboards take a while to be upgraded to the latest interfaces. So we're still stuck with VGA here. We have host USB ports, 4 of them at the back, and a device USB port, so you can connect this to an external computer so that it can be controlled via USB, and LAN, of course, serves a similar purpose. At the top we have the external reference coming in and the 10 MHz reference coming out. These two ports are available independently from each other, and then we have the SNS series noise source or the 28-volt drive pulsed for the external noise sources as well. So if you have a smart noise source, this would obviously be the way to go, and I have one of those, so we're going to try it out. For the rest of the BNC connectors, we have 2 trigger inputs, 2 trigger outputs, and a sync port used to synchronize and trigger external instruments or trigger the spectrum analyzer from an external event. Then there's the analog output port, which can be configured as like a video output or directly the demodulated audio if you have those options installed. And then there's a digital bus, which is an expansion port for other things. I don't have anything that connects to that right now. There's the power line coming in and the auxiliary IF output, which is the wideband IF output exceeding 100 megahertz of bandwidth. And we're going to take a look at that hopefully in one of our experiments once we get it working. So this is at the back, pretty straightforward and exactly what you would expect from this instrument class. Now, even though this instrument runs Windows 7, and normally that computer itself boots very quickly, because of all the application that's loaded on this particular model, this is a fully loaded one, it has everything on it, it actually takes quite a bit of time to boot up. So this is not a type of instrument you're going to turn on and off in between your measurements. This is something that people typically leave on, so I'm not going to wait on camera for it to boot up, but it's going to have to go through all the applications preloaded, and it's going to go through all of its internal alignment for the first time it starts up, and that's normal for all the spectrum analyzers. Here we go, we're all up and running. Now, in order to capture the screen, instead of filming it directly, I'm going to install the screen capture program to run on the spectrum analyzer directly. And that's going to be quite helpful because I think it's going to improve the viewing experience, since it's very difficult to get the focus and the lighting correctly this way by filming the screen. Also, what I've done is I've connected the source here, the EXG vector signal generator, directly with the USB port to the EXA. This allows the EXA's source control software to control the EXG directly, and as well as the fact that I've connected the triggers at the back together, so this improves the speed in which they can communicate and start and stop measurements quite significantly, and we will see that in action. Now, instead of just showing you all the different things on the spectrum analyzer, I have devised a very elaborate experiment which we're going to go through, and in the process of that experiment we're going to learn all the different functionalities and capabilities of the EXA spectrum analyzer here. So let's go ahead, take a look at the setup that I want to actually measure and look at all the different components, and we're going to come back and take it apart and look at it one step at a time and really understand what's going on. So let's take a look at our experiment setup. Now, this is going to be a wireless transceiver with a sliding IF with a super heterodyne architecture. So let's take a look at it one step at a time in order to understand what it is that we're going to be testing. Our transmitter starts with an arbitrary waveform generator, which is connected to a single sideband mixer. Now that's going to bring our spectrum to a frequency at around 500 megahertz. Now I want to bring that even higher in frequency, so I'm going to use a double sideband mixer connected to a PA, which then ultimately drives an antenna. Now this mixer is going to require its own LO, and that LO is going to come from a 6 GHz PLL. Now this configuration implies that if I use a 6 GHz PLL here, I'm going to have spectrum on around 6.5 GHz and 5.5 GHz coming out of the PA here. So I want to receive that now. And on the receive side, I'm going to have again an antenna, a low noise amplifier, and another double sideband mixer right over here. And of course, that's going to require its own LO signal. But since this is a sliding IF configuration, we're going to use an EXG vector signal generator from Keysight, whose output is connected to a doubler and then amplified before fed into the mixer. So now the output of that can go back onto a single sideband demodulator right over here, and then we're going to get our I and Q signals back at the end. This is itself going to require an LO signal, and that's going to come from another PLL that's going to run around 1 gigahertz. Now, if you notice, what is missing in this setup is that we don't have any filtering, and of course that means that we're going to have a whole bunch of spectrum in the frequency band which we may not want, and that's going to be something we can take a look at, and we'll see the consequences of that as well. Now, where does the EXA fit into all of this? Well, every single one of the components in this setup needs to be characterized in some way, and the EXA is capable of doing that. So we're going to take a whole bunch of different components and we're going to characterize them using the EXA so that we can understand their performance, and each of the performance of these components obviously is going to impact the overall link budget and the system performance of this transceiver. So there's a lot of different things that I would like to test, and we're going to start with something very simple, and then we'll take apart this setup one step at a time and characterize each component, and there's a lot of really cool and interesting things that we can learn from that. So the first component we're going to characterize is going to be this frequency doubler. And right now I have it connected to the EXG at the bottom and connecting the output directly to the EXA. And just to remind ourselves, that's the doubler that's going to be used on the receive side on the double sideband mixer. So let's go ahead and take a look at what happens when we put some signal into it and how we can use the combination of the EXG and the EXA to characterize it. So let's jump to the screen. And here we're looking at the spectrum of the spectrum analyzer, of course, and I don't have the EXG enabled yet. I have set the EXG to be at 3 GHz with an output power of 0 dBm. Let's go ahead and turn it on. And there we go, and you can clearly see the main tone coming out of here. This tone is going to be at 6 GHz, and this is the feed-through tone. Normally you don't want this in a doubler. You want that to be as small as possible so that you can have a clean double tone, and of course that's not quite possible, so you're going to have some feed-through. Now if I go ahead and press the peak search function over here, you're going to see that the instrument will report, of course, the maximum peak and at minus 27.3 dBm. Now I can go ahead and increase the power into the doubler from my synthesizer down here, and you can see as I increase it, we're going to get stronger and stronger fundamental tone. Now I'm at 6 dBm, and you can see we are also going to see the third and the fourth harmonic to start coming up, and we have some rejection of the fundamental, and we'd like to characterize that. Now I can also go ahead and change the frequency. So right now, as I said, we're at 3 GHz. Let's go, for example, to 3.5 GHz, and you can see all the tones will move synchronized with each other as to be expected. But if I want to characterize this doubler, I don't want to sit there and put every single frequency and then measure the tones. Well, since we have the EXG directly connected to the EXA, we can actually use the EXA's source control functionality to do a characterization of our doubler. And we can do both the fundamental and the double tone because we can do offset tracking from the source control. Let's take a look at that. So let's characterize the fundamental feed-through of this multiplier. Now this multiplier is rated to operate between 2 to 4 GHz at the input, so we can go ahead and change the scale accordingly. I can start the frequency at 2 GHz and I can stop the frequency at 4 GHz. And of course now we're going to be able to see our fundamental tone right here in the middle. Now let's go ahead and turn off the synthesizer for a moment and configure it in the source control option. Now if I click on source or press the button right over here, you can see all my source control here. Now the source has already been selected right over here, and it's actually listing it as an MXG, which is unusual because this is not an MXG, it's an EXG. I don't know why it does that. But nonetheless, the source is right over here. It's detected the correct one, is connected via USB, and you can see that the connection has been verified. So we have our source control nicely up and running. Now I want to characterize the fundamental frequency, so the same frequency going in and the same frequency coming out. If I click on frequency here, it gives me the option to do an offset tracking. Now here I can do a multiplication on the numerator and a multiplication on the denominator. So obviously 1 over 1 is 1, which means that it's going to track the EXG 1 to 1 with this start and stop on the RF frequency at the bottom, which is exactly what we want for the fundamental frequency. Let's go back to source. Now what about the amplitude? Well, we're going to operate this multiplier with quite a large input signal as it is required for passive multipliers like this. So we're going to go ahead and change the amplitude to 10 dBm. So now it's going to put a constant 10 dBm into the multiplier. Let's not worry about power sweep. We're going to use that later for something else. We're going to go back to source. Now everything looks good. Obviously it's turned off, so you can see that the source mode is off right now. Now I'm going to go ahead and turn the RF output on. Now the first time you're going to turn it on, because it has to synchronize and it has to reset the source, it's going to take a couple of seconds for it to do that. Right now it's resetting the EXG and configuring it with everything, and there it is, it's up and running. And this trace that you see over here is the actual measured output power at the fundamental tone while the EXG is sweeping the input. So basically it's a tracking generator now. Now you may ask, well, how do you know this power is accurate? You didn't do any calibration, you didn't do any normalization of the input, because normally you would want to connect the output of the EXG directly to the input of the EXA and then do normalization. Well, I skipped that step because we don't care so much about the accuracy of this power. But don't worry about it, you can easily do it. In fact, there is a very nice way to do it. If you click on trace and detector and you continue over here, you can see that there is a normalization option. And if I click on normalize, in fact, you can do a proper open short calibration. And if you click that, the instrument will give you instructions on how to connect your external source to the EXA, MX, or any kind of spectrum analyzer that you may have, and you can do a proper calibration so you can get accurate relative gain measurement. But we're skipping that because we don't really need it. Now if I go back to the frequency, what this is telling us is that if I put a 10 dBm signal into the multiplier, I'm going to get about minus 30 dBm output power, just a little bit higher than that. So we have roughly about maybe 40 dB, maybe 35 dB of fundamental rejection. And that's nice and great, but this doesn't tell us how good the multiplier is performing, because the actual rejection is going to be the power coming out of the doubled compared to the fundamental. So we still need to do another test to figure out. We can do exactly the same thing, except now do an offset tracking, so we should be able to see what the efficiency of this multiplier is. And all we need to do is to record this number down. You can also save the trace on the screen if you want to and compare it with the next measurement, but it's going to be easier this way. Let's remember this number roughly around minus 30 before we move on. Now we can go ahead and change the settings to measure the other parameter. Just one other thing I wanted to point out, look at how fast this is. I mean, we're sweeping from 2 to 4 gig, 201 points, and the synthesizer is doing a tracking generator with everything connected at just under 0.3 seconds. So it's really, really responsive, which is very important if you're going to do lots of points and you're going to keep doing different measurements that have a dynamic behavior. So let's go ahead over here. Let's turn our source off. Since we don't need it anymore, obviously the trace is going to drop because we don't have anything anymore coming out, and I'm going to turn the tracking also off. This is going to now reset the synthesizer, so now we can go and get back to our normal spectrum exactly like we were doing before. So let's go over here now under frequency and change our denominator by a factor of 2. So this means that now the input is going to be at half the frequency of what the RF frequency is shown at the bottom. This is exactly what we want because we want to measure the doubled frequency. So now I also have to go ahead and change my start and stop frequency. Now we can go from 4 gigahertz and we can stop at 8 gigahertz. Now we're going to be looking at the doubled output. Let's go back to the source control once again, and let's go ahead and turn it back on. This is the same input power as we had before. It's going to put 10 dBm into it again, except it's going to look at the signal between 4 to 8 gig and the input between 2 to 4. Now let's resetting the source one more time, and there we go, and check it out. We have a much better response than we had before. So you can see that there is a little bit of a ripple, and that's most likely due to some impedance mismatch. The output of this multiplier, which is on just a very cheap, inexpensive PCB, but then we get a much better flat response. Now if you look at an average value here, let's put a marker on it. Right here in the middle, you can see that I'm getting minus 5 dBm. So I'm putting 10 dBm in, I'm getting minus 5 dBm at the doubled frequency, and I was getting about minus 30 at the fundamental. So we have roughly 25 dB of fundamental rejection in dBc compared to the doubled frequency. And this is very useful. I just managed to very quickly find out exactly the behavior of this doubler to give me an idea of what kind of rejection I can expect. This will tell me whether I need a filter or not, and other system parameters will depend on that. But then you may ask, well, how much power should I put into this doubler? Is it worth to keep putting more and more power into it to get more and more power out? At what point is it not worth it anymore? Well, for that, we need to do a power sweep and not a frequency sweep. And in fact, we can easily do that using the source control as well. As I mentioned, we have power sweep capability. So now we're going to choose a sender frequency, and based on the sender frequency, we're going to do a power sweep so we can see the efficiency of this doubler as a function of input power now. So let's go ahead and do our power sweep. First, I'm going to turn off the output of the RF source one more time and disable the tracking. And now I want to characterize the doubler at a fixed frequency, and I'm going to do that at 6 GHz because that's the frequency that I'm interested in running the double sideband mixers on. And we can do that by making sure that the center frequency is indeed set to 6 GHz, and it is. And we're going to change our span to be 0 span. So now the x-axis of the spectrum analyzer is in time and it's not in frequency anymore, continuously measuring the power at 6 GHz. Now let's go and configure the source. Under source, we're going to go under amplitude. Let's change the starting amplitude to minus 10 dBm. So it's going to start sweeping the power from minus 10 dBm. And how much is it going to do? Well, here I have entered the power sweep range, 35 dB. So it's going to go from minus 10 dB, m plus 35 is going to be 25 dBm. And 25 dBm is no problem for the EXG because I have the high power option installed on the EXG that I have here. So let's go ahead and enable the power sweep. Let's go back and check one other thing. Let's change the frequency, and you can indeed see that we have 1/2. So the EXG is going to stay at 3 GHz and sweep the power from minus 10 dBm to 25 dBm, and the EXA is going to plot the input-output power relationship, which is exactly what we want. Let's go ahead and enable it once again, and based on that plot that is going to be generated, we can decide how much power we want to put into our multiplier in the final system. Now it's doing the reset on the EXG one more time. I'm not sure why it has to do the reset each time. Oh, and we're actually going outside the screen, no problem. Let's change the input level all the way to 10 dBm and check it out. This makes perfect sense because it means that at very low input powers, remember here at this left corner we're at minus 10 dBm, and here at the right corner we're at 25 dBm. So at the very, very left, we are getting basically a very linear relationship between input and output power. But at some point, this passive multiplier simply cannot give us more power, no matter how much more power you put into it. In fact, if you continue on, you're going to destroy it. So if I put a marker on this and I go over here, I can see that, well, you know, for a reasonable input power, you know, under 20 dBm, around 50 dBm or so, I can get almost 2 dBm out of this multiplier. But that's not enough for a double sideband mixer, and this tells me that I am indeed going to need to put an amplifier after this multiplier to really be able to take the most out of it. And all of that in one setup. I haven't touched the setup at all. All I've done is just pushing the buttons on the spectrum analyzer. And one other thing to note is look how fast it sweeps. Again, we're sweeping from minus 10 to 25 dBm at 201 points, and it happens in, you know, about 0.1 second. It's very, very quick, and I appreciate that because if you're doing a lot of measurements, the last thing you want to do is wait for a slow instrument. So I think that's pretty good. Now we can move on to our next module. And here, for the sake of completeness, you can take a look indeed at the EXG sweeping. You can see that it is fixed at a 3 GHz frequency and it's on remote connection and the power being swept. Now obviously this is not going to show you as fast as it is sweeping because the display doesn't update as fast as that, but you can clearly see that the system is exactly like it was when we started, all in one place. So the next component I like to characterize is this LNA. This is a broadband amplifier and it's supposed to have simultaneously fairly good noise. So I'm going to try and using it as an LNA. Now because it's so broadband, I don't expect this noise figure to be very good. It's not going to be something like a dB. It's going to be much, much worse than that, but nonetheless it might be good enough for this application. So we would like to characterize that. Now in order to measure the noise figure of the amplifier, I'm going to use this SNS N4002A noise source from Keysight, and this is a noise source that goes from 10 MHz to 26.5 GHz, and it has an ENR range of about 12 to 17 dB. And the nice thing about the SNS noise sources are that all the ENR table values are stored electronically inside the noise source. And as soon as you connect it to the instrument like I have here, all the ENR table values will be downloaded into the spectrum analyzer, and you don't have to do that manually. This is a big advantage because that's a very, very annoying thing to have to do each time you connect something, and sometimes table gets lost and you could enter it by mistake. It also has temperature compensation built into it. The SNS noise source like this one, the 26.5 gig one, is about $4,000. So we can go ahead and use that to measure the noise of our LNA. Now, as to remind ourselves, the LNA sits right over here, and then it's going to be followed by a double sideband mixer. So I'm also interested to measure the noise figure combination of the LNA and the double sideband mixer, because this will tell me how much of the noise figure of the mixer is still visible after the LNA is connected, if the LNA gain is not high enough or its noise figure is sufficiently low, for example. So that would be one thing that I'm very interested in figuring out, and those are the two things we're going to do using this noise source. Now we have to set it up, of course, and connect it to the instrument and go through the calibration process, but let's go through that and see how the instrument handles how easy it is to measure these type of noise sources using the EXA. So let's go ahead and configure the EXA for noise figure measurement, and we can do that by pressing the mode button and select the noise figure application. Now this has a lot of applications built into it because this is a fully loaded unit. You can see there's 6 pages in here. We're going to continue down the pages until we see noise figure, and here it is. Here's our noise figure application. We're going to click on that. And there it is, it switches to the noise figure application. You should notice how fast it is, and this is because all the applications were loaded at the time of startup, and you can switch back and forth between them very, very quickly. Now obviously this noise figure measurement right now is meaningless because the unit is not calibrated. You can see that the calibration is invalid right now. Now what is the range of frequencies I want to measure? Well, I've already entered that. I'd like to measure this amplifier from 500 megahertz all the way up to 8 gigahertz, and that's actually going to operate at around 6 gigahertz, but this is going to give us a very good view of its noise figure as a function of frequency. Well, now that we have this input frequency, how do we calibrate this system? Well, let's just check a couple of things to make sure everything is in order. Let's make sure that the noise source is working. If I click on the ENR, you can see that I can go under noise source setup, and in fact the noise source has been selected. It's an SNS noise source and it's been detected, and all the ENR table has already automatically been loaded into the instrument. I don't have to worry about any of that. That's great. Now let's click on mode setup. And under mode setup, we can go under DUT setup, and here the instrument would tell us what we need to do in order to do our calibration and to do our measurement. So it's showing us this view here. It's saying if you want to calibrate the instrument for an amplifier measurement, remember our DUT is an amplifier, you can select other things, and we will do that later. And if you want to just measure an amplifier but at the same input output frequency, it's really straightforward. Just connect the noise source to the input of the EXA and then calibrate. And if I want to do the measurement, well, you're going to have to insert your DUT between the noise source and the instrument itself. So it's really, really straightforward. Now that we know how to do this, I've already done that. I'm already in the calibration mode. I've already connected the noise source to the input of the EXA. Now we can go under measurement setup, and we can actually click calibrate. Now there's one other thing I want to make sure. Yep, I just wanted to make sure that we have enough points. I have set 25 points, so it's going to do 25 points between 800 to 8 gigahertz, which is great. Now back to measurement setup, and I'm going to click on calibrate. Now it's asking me, are you sure you want to calibrate? Indeed I am. Now it's going to go through the calibration, and it will go through different frequencies, and it's going to de-embed the impact. Oh, interesting. That actually failed. It's never failed before. That's unusual. Let's try it one more time. I wonder why it failed. Maybe a bug or something wrong with the application. It's never happened before. Here we go. Now it's working. I'm not sure what happened there. I didn't change anything. But anyway, so you can see that it's now calibrated, and it is measuring the gain of whatever is connected between the noise source and the instrument. And right now there is nothing connected, so you can see that we are basically sitting at the error floor of the noise figure personality capabilities. It's telling me that the gain is 0 dB, which is correct, and it's saying the noise figure sometimes goes below 0, but this is within the accuracy of the unit. So we are no problem over there. We can go ahead and now disconnect the noise source from the instrument. And if I do that, obviously the noise figure is going to get saturated because there's nothing connected to the noise source, so it's like an amplifier with a huge attenuation. So now what we need to do is we need to connect the amplifier between the units. So let's take a look at how we can do that. And here is our measurement setup. The noise source connected to the input of the LNA, the output of the LNA taken directly to the input of the EXA. So everything is ready, it's not plugged in yet, and as soon as I apply power, we should be able to see the effect on the noise figure. Let's take a look. So let's go ahead and apply power to the LNA and see the effect on the noise figure. Here we go. Is plugged in, so the instrument is going to automatically auto-scale everything, and there it is, it did that. And I've already placed 2 markers on the noise figure and the gain. Now if you look at the gain of this amplifier at the very low frequencies is about 37 dB, which is exactly what it should be. This is correct, that this gives us confidence in our noise figure measurement. Now if I continue, you can see the gain is dropping linearly with dB roughly, and then there's a notch in the frequency response, and that notch in fact is real. Is a problem with the output matching network of this particular LNA. So at about 6 GHz, we have 18.2 dB of gain. And if you look at the noise figure is pretty good at low frequencies, just under 3 dB, and at the frequency of interest at around 5.8 GHz, the noise figure is in fact around 4.7 dB, which is not that great, but it's also not terrible. It should be able to do what we want with it. Now the question is, how is the noise figure of the system going to be affected by the mixer? And then the only way to do that is to connect these guys together and find out the effect of this mixer on the noise figure of this LNA. The other thing to note is that the input, the gain drop here, this notch does not show up in the noise figure, and this is indication that this notch is indeed from the output matching network and not at the input. Otherwise you would have seen that added to the noise figure. So everything looks good, I would say. Now we can move on and try and measure the combination of the LNA and our mixer noise figure together. So now our setup is becoming more complicated. Now I'm going to measure the noise figure of the mixer along with the multiplier and the LNA, and that's going to be our noise figure of our receiver, pretty much very close to what is going to be in the final setup. So let's take a look and see what's going on. The output of the EXG, which is our synthesizer, goes through the doubler, then goes through an amplifier, and the amplifier output is going to be the LO signal. This means that the synthesizer only needs to sweep at half the frequency because we have a doubler, and the output of that goes directly to the LO of our mixer. And I'll show you the mixer a little bit closer. The mixer is an Avantech mixer which works between 2 to 8 GHz. And the input, RF input to the mixer comes from our LNA as to be expected, and the IF output is then taken out, which then is of course fed to the EXA. So the entire section at the bottom here is what I have built. So we're getting closer to the final system. Now we can go and take a look at the screen to see what's going on. Let me just give you a quick close look here as well, so you can see that indeed we have our mixer and LNA connection made and the LNA has been turned on. So if we go and look at the screen, I can show you how the instrument needs to be configured in order to be able to do this measurement. And here we are back again at the DUT setup menu, and you can see that once I've chosen the down converter option here, this DUT has been updated to show us what a down converter noise figure measurement setup should look like. And indeed it's very straightforward. We have the noise source again connected to our mixer and the LO being applied to the DUT and the IF then taken back onto the EXA. And here's a spectral view of what that's going to look like. I'm measuring the upper sideband noise figure here. I'm not going to go into too much detail with the differences. I'm assuming that if you're watching this that you're somewhat familiar with these concepts already. And I'm doing a sweep on the LO frequency, which means that the RF frequency can also be swept. And this is going to result in a constant IF frequency. I've chosen an IF frequency of 333 MHz. This is the first stage of the super heterodyne down conversion of our receiver, so this is a good frequency, roughly where we want to use it, so we can start with this. It's not a problem. And since our RF is swept from 5 GHz to 7 GHz, right around the frequency we want to use the receiver as, the LO can be swept between these two frequencies. But let's not forget that we do have a multiplier, which means that the LO should run at half this frequency. And in fact, we can easily set that up also, because the LO is going to be provided using the EXG. The noise source personality can also control an external source, and in fact, this is exactly what's going on. And if I go under mode setup, and if I go under external LO setup, and I can go ahead and change the LO setup here, you can see that I've chosen the LO power to be 10 dBm, and we know this from the previous measurement we did where we measured the multiplier's efficiency and so on, and I have set the LO to have a multiplication factor of 1/2. So it's going to sweep the LO at half the frequency of the RF, exactly as to be expected because we have a built-in doubler. Now if I go under measurement, everything's taken care of, and I've done a measurement right over here, and you can see that the gain is lower than it used to be, and that's correct because this mixer is a passive mixer and it's going to have some conversion loss, and around around this frequency, you can see that we have a couple of dB of conversion loss. We're at about 16 dB of gain. And the same dip that you saw in the frequency response of the LNA is still present here, as it should. And the noise figure, luckily, hasn't been much affected. We're around about 4.7 dB, 4.8 dB like we were before, except for the fact that we have a little spike over here which I could not get rid of, and I suspect it has to do with the interaction between the mixer and the LNA. You can see it lines up right over here when the output of the LNA is not very well matched, and I suspect that because the input of the mixer is also not very well matched, that there is going to be some interaction and some problem rising. But this is exactly the type of results you're looking for to find potential problems, and now you can go back, measure these components individually, and potentially find what's going on and correct it. But for the purposes of this experiment, we know that this is going to be a fairly reasonable receiver. It's not earth-shattering or anything, but nonetheless we can easily measure it. You can see the software is definitely designed to allow us to do this very quickly. So now that we have this portion, let's now turn our attention a little bit toward the transmitter and see what we can do over there. Now if you recall, the very first stage of our transmitter is a single sideband block here, which has a built-in arbitrary waveform generator giving us our first stage of up conversion. And for that I'm going to use this Signalhand VSG25A, which is basically that block built into a box that you can program and configure from your computer. And this thing works from 100 MHz all the way up to 2.5 GHz, and we intend to use it around 500 MHz or so. So there's a lot of stuff that you can use the EXA for to characterize this alone, and we're going to take a look at some of those things to get an idea of how well this thing actually performs. And once we have characterized this, then we have a fairly good idea of what the starting point of our transmitter is. So as we go along the chain here, we can see the degradation of the signal due to the impairments of all the other blocks. So let's go ahead, hook this up to the EXA and turn it on and see what we can do with it. Here we go. I've gone ahead and connected the VSG25A directly to the EXA, and I've actually reviewed Signalhand products in the past, so I recommend that you go and check them out. I was impressed with their other products, so now we're going to characterize this. Now this is also a USB controlled instrument, and it has its own software that runs on the computer. So let's go ahead and launch the software, see what kind of stuff we can do with it, and then that will help us to plan out how we're going to characterize it using the EXA. And here's a quick look at the software for this vector signal generator. I'm not going to dwell on it too much. I apologize for filming the screen. I just wanted to show you where I will be controlling the unit from. So I'm going to use this to generate multi-tones as well as various constellations, so we can use the EXA to characterize the performance of this vector generator. So let's go back to the EXA and see what we get. Now, since we intend to use the Signalhand vector generator at around 500 MHz, it makes sense to start by looking at the signal at 500 MHz. And that's exactly what I've done. I've configured it to generate the tone at 500 MHz, and let's go ahead and enable that tone. And the power is set to 9 dBm. So let's increase the amplitude over here to 10 dBm. And you can see that this vector signal generator actually puts out quite a lot of tones outside of its own main fundamental tone. So it might be good to put a filter after this before we feed it to the double sideband filter, in order to make sure that these tones don't interfere with the double sideband filter's performance, because they are still within its bandwidth. So let's go ahead and change the frequency span a little bit and look at only the frequencies that we are interested in, and up to 5 GHz you can see the tones there. Now I've also configured the instrument to generate two tones at 10 MHz apart, centered at 500 MHz. In order to be able to measure the output OIP3 performance of the vector modulator. And I can go ahead and enable that as well. And as soon as I do that, we see a whole bunch of other tones, indicating further that indeed having some filtering would be beneficial. Let's focus a little bit closer at around 500 MHz. So I'm going to put a center frequency of 500 MHz, and I'm going to change the span to be small enough such that we can begin to see the tones. There they are. And let's reduce the resolution bandwidth to 30 kHz. And look at how fast this instrument is. I mean, we are spanning 100 MHz with a 30 kHz resolution bandwidth and video bandwidth, and it only takes 2.7 milliseconds, which is great. Very fast. I really like that. And of course, if I go ahead and do a peak search, you can see that one of our main tones is at 495, and then the other one, I can click on that, and oh, let me just actually move it. Where are we going? Around, should be. There it is. Oh, it's very hard to get it. Come on, you can do it. There it is. 505 MHz sitting on these two locations. So it sounds perfect, and we can see our intermodulation products. Another thing to note is that it's asymmetric, and it has to do with the phase of the internal DACs, as well as how the frequency planning architecture is. But this asymmetry can be sometimes problematic, but you can see that our lower sideband doesn't exactly look like the upper sideband. So now I want to calculate the third order interset point? Well, there are a lot of built-in measurements into the EXA, and you can see a whole list of them over here, and there is also a second page, and there is a built-in TOI. So if I go and select that, the instrument actually resets its x-axis and vertical axis and so on, which can be a little bit annoying. So let's go ahead and change the reference amplitude to 10 dBm and reduce the span once again so we can see our tone, reduce the resolution bandwidth down to 30 kilohertz, and the instrument automatically picks our intermodulation products and our main tones, and it does all the calculation for us. And it's saying that the third order interset point is about 25 dBm at the output, which is not too bad, it's reasonable. And you can see that our third order intermodulation products are 40 dBc below the fundamental. And this gives us some really important information about how the system will behave in the presence of modulation, which is what we are interested in using. So if I go ahead and now reconfigure the vector modulator for to produce a QAM modulation, we should be able to observe that as well. And that's in fact exactly what I've done. I'm going to go ahead and enable the modulation. Now the modulation is going to be a 64 QAM at 25 mega symbols per second with a root raised cosine filter coefficient of 0.35. So you should know exactly what that looks like. We can go ahead and apply it, and there it is. Now let's get out of this measurement capability because we don't want to do this inside this measurement. Let's go back to the swept spectrum analyzer, and you can clearly see our spectrum centered at 500 megahertz with the modulation on top of it, and the third order modulation products on the sides are going to occupy the adjacent channels. Now we can go ahead again and use some of the built-in functionality to measure some of the properties of this spectrum. If I want to find out how much power is being transmitted in this modulation, I can do that by using the measurement function channel power. Now I've already configured channel power by entering the center frequency and the integration width that I'm interested in, and you can see that it's integrating over a 35 megahertz bandwidth, and it's saying that the power is 8.1 dBm, which makes sense. I'm transmitting 9 dBm and there's some losses and so on involved, and the power spectral density is also given to me. I can also go under display and enable the bar graph so you can see exactly the portion of the spectrum that's being integrated. And this is an important measurement obviously because you want to know how much power you're going to transmit. Well, and how much bandwidth am I occupying with this transmission? Well, we can also measure that really easily by clicking on measure and going to occupy bandwidth. And you can see that I've already configured this as well by centering it at 500 megahertz. And you can see that it says that the occupied bandwidth is 29.2 megahertz, and that will include 99% of the total transmit power, and it matches the measurement we were doing before. It also tells me that at a 30 dB drop, so 30 dB below the main power transmit, you can see that I'm occupying 33.8 megahertz. All of these are configurable obviously through different measurement setup configuration. So if I go ahead and change my modulation filter at the vector generator, instead of having a 0.35 alpha for the root raised cosine, and I go to a 0.22, I expect the occupied bandwidth to get smaller. Let's try it out. There you go. And indeed, you can see that in fact it does go down. So it is perfectly consistent. You can quickly do these measurements right on the spot. So how much power am I putting out in my adjacent channels that you can see here, and that's of course undesired? Well, I can measure that too because we have adjacent channel power measurement, and I've already configured it, and there it is. You can see that I'm measuring the channel of interest, which is my channel. There's some guard band in between my channel and the adjacent channels, and it is calculating the total power in the adjacent channels, and it's giving it to me here in the table. And since I have only one carrier here, it's doing it only for one carrier, but you can do it for as many carriers as you want. And not to mention that you can actually give it a radio standard. Any of the radio standards that are currently used in the industry, you can configure, and then it will do all the settings for you, which can be a huge advantage. Since this is a completely custom carrier, we're just doing something ourselves. That's why I've configured it manually myself. Now, because I'm putting out so much power in the adjacent channels, I can go ahead and reduce the transmit power so that the nonlinearities don't generate so many intermodulation products. So I'm transmitting 9 dBm. Let's go ahead and transmit 3 dBm instead, and take a look at what happens. You can see that in dBc, we have our adjacent channel power significantly improve, and this is to be expected. So perhaps maybe this is where we want to operate to avoid putting out a lot of emissions in the adjacent channels, and this would be a good start. And well, now let's get serious. Let's go ahead and launch the VSA software from Keysight, which this instrument natively supports, and see what it looks like. Now I've already loaded the VSA and configured it so that I don't have to show it on the camera here, but I want you to see how fast it is. So everything is already loaded, so I can press mode and I can say I want the VSA, and it just comes right back up. And look at how fast it is. I mean, this is direct hardware access. I am analyzing 4096 symbols of the 64 QAM constellation, and I'm doing all the calculations, everything live here on the screen while simultaneously doing a screen capture, and it is ridiculously fast. And of course it's because it's directly connected to the baseband processor board that I showed you, and the performance of this vector signal generator is not too bad. You can see here at the bottom left I'm looking at the spectrum centered at 500 megahertz, and I'm looking at a power of 2 dBm because I reduced my power transmitter to 3 dBm from the instrument to reduce the adjacent channel power as we just saw. And here's our constellation. Looks really clean, and here is our EVM as a function of symbols. You can see I'm stopping at 4095 or 96 symbols over here, and this shape of it, there's a reason why this shape is present. I'm gonna let you think about that. You can talk about it in the comment section, but there's a very subtle reason why this happens. And if you look over here, this is our modulation performance, and if you look, we have an EVM of 1% and an SNR of 40 dB. For a 64 QAM, an SNR of 40 dB is just essentially error-free. So this is a completely error-free transmission, very clean constellation coming from the VSG25A. Pretty impressive. And you can see the effect of the noise, phase noise on this is completely non-apparent at all, because the phase noise at 500 megahertz for the VSG25A is very low. And I can go right back directly to the spectrum analyzer, and it just comes right back up. It's pretty convenient. I really enjoy the fact that you can jump back and forth so easily between these softwares, and it's up and running for you. So now that we have this, and we know that the phase noise is not a problem at 500 megahertz, but there's no guarantee that it's not a problem at 6 gigahertz, because we still have to have a PLL to drive our double sideband mixer, which follows this. So now let's go and take a look at the PLL and characterize its phase noise. And here's a look at the PLL we will be using. This is a product from Hittite. It's an HMC 700 series product. It's actually a 2-chip solution where you have the PLL core in one IC and the VCO in a different one. And you can see the block diagram right over here. We have an external VCO, and the loop filter is of course also external. The phase frequency detector, all the different fractional dividers and prescalers and so on are what's on the PLL, of course. And then you have the crystal reference from the outside, which is a 50 megahertz, and I have the evaluation board right there. Let's take a close look at it. And here it is, the main Hittite HMC 700 part sits right there. That's the PLL core. We have our external VCO right there, which completes the loop in the feedback path right there. Here's a 50 megahertz crystal externally, which has a very good low phase noise, and that's used as a reference for the whole system. And this is the VCO output. This board right here is just used to configure this, and this runs from a single 5.5 volt power supply, and you can program it using SPI with this SPI to USB converter with a GUI that runs on the computer. Now the reason we want to use this and play around with it, I want to find out what configurations of the PLL chip is going to give us the best phase noise, so we can program the chip like that. This supports both fractional and as well as integer divisions in the PLL loop, so we can see what the impact of that is on the PLL performance itself. I'm interested mostly in the integrated jitter, which has the highest impact on the EVM of our constellation. So let's go ahead, plug it in, take a look at it. And here is our setup in action. I have the synthesizer directly connected to the instrument, and here I'm running the GUI software that allows me to configure the synthesizer IC. And you can see that I can load different configurations on there, and we can examine the impact of those settings on the phase noise of the PLL. And here is our tone, of course. You can see it is locked at 6 gigahertz, and you can see the second and the third harmonic of our output of our PLL, which is not that important for us. So I want to see the phase noise here. Well, we have a built-in phase noise personality. It's one of the applications available. So let's go under mode and let's advance until we find phase noise, and here it is. Here's our phase noise personality, and we click on that, and I've already configured it. The configuration is pretty straightforward by giving it a standard frequency. So what I'm doing here is I'm sweeping the phase noise, measuring it from 100 Hz offset all the way up to 100 megahertz of offset. And you can see a very classic PLL shape of the phase noise. I have the marker set at 1 kilohertz, and you can see we're measuring about minus 88 dBc per hertz at a 1 kilohertz offset and a 6 gigahertz carrier. I can also go under these measurement settings over here, and I can then go on to the second page and enable the decade table, and that will just give us a nice measurement of the phase noise every decade offset from the carrier. And you can see that this is actually a very good PLL. We are reasonably close to the limit of the instrument itself, so part of the limitation here is now becoming the EXA. So if you're looking for really good phase noise measurement, the EXA may not necessarily be what you're looking for. Of course, remember that this is a very clean PLL, and having a phase noise of minus 90 dBc per hertz at a kilohertz offset at 6 gigahertz is very respectable. So right now we're still above the phase noise of the instrument, so we should be able to detect some changes in the phase noise and see the behavior of this curve change depending on how we load the settings. So let's go ahead and calculate the total integrated jitter of this PLL under the current settings. Right now the PLL is in fractional N mode, and I like to see the difference between that and its integer mode, and I expect the integer mode to have a lower phase noise, and we can find out. So let's go ahead and do that calculation. I'm going to go under marker function, and I'm going to choose integrated RMS noise in degrees. Now I like to look at it in seconds, so I'm going to change the unit to seconds. There it is, and I need to adjust the band under which this calculation is being performed. So I'm going to set the left band all the way up to at 100 Hertz, so all the way to the left, and the band on the right at 100 megahertz, which is all the way to the right. And you can see that it's giving me an integrated jitter at 248 femtosecond for this entire band, which is respectable. That's not too bad. And so now we can go ahead and change the settings. There's one other thing that I want to do. We can actually do a noise floor extension because this unit is equipped with that, and that's going to improve the noise floor here a little bit. And I can go under mode setup, and there is noise reduction right here, and I'm going to go ahead and enable that. And if you pay attention, once it runs, you can see that we get a little bit of boost here, so we can go all the way down to minus 150 dBc roughly here at the bottom here, and it doesn't have too much of an effect on the jitter there because the jitter is dominated in this region. So now that we have this and you're taking a look at these numbers, let's go ahead and change the PLL mode to jump from fractional N to an integer type of approach. I'm going to go ahead and load that, and there it is. Now you can see the PLL will reset, and check it out. You can see the behavior actually changed significantly. Our phase noise improved by about 3 dB at 1 kilohertz offset, and improved universally all the way to the PLL bandwidth here. And you can see that our jitter peaking actually also improved, and our integrated noise went down by about 50 femtoseconds for the same section of the offset. So this indeed has an improvement, which means that I would like to use the PLL under this condition. So this is a very quick overview, of course, of the phase noise personality. There is also phase noise cancellation, which I'm not using, which you can have a reference phase noise plot and then subtract and do all kind of fancy calculations. This is just an overview for you to see how quickly you can get some really important measurements about the shape of your phase noise. And this is a industry standard phase noise personality, which I'm sure you've seen before. So now that we know this improvement, we can go ahead and build our overall transmitter. So then we can connect everything together and see what the signal looks like at the end of our transmitter, and then finally build the whole system. And here we have our transmitter put all together. At the very beginning we have the IQ modulator up to 500 MHz, so it's running at 500 MHz right now, and it has the QAM constellation on top of it, going on to a low-pass filter, and finally to the double sideband mixer. Now the LO of the mixer comes originally from the synthesizer that we just measured, and I've configured the synthesizer with settings that gave us the best integrated jitter based on the phase noise measurement. The output of that is amplified before it is applied to the double sideband mixer so that it would be within the LO requirements of the mixer. The output of that, which is our RF transmitter, has around 6.5 gigahertz. It's going to be amplified by this PA before it is finally sent to the network to the spectrum analyzer right now. And all these things are configured obviously with different computers around the lab, providing the settings and the modulation format and so on these different things. And the power supply for the
PAs and the LO amplifier and the synthesizer are coming from different places. The power supply of the PA is provided by the Keithley power supply right there. You can see 12 volts consuming 53 milliamps. And all the way on the left over here, the power supply for the synthesizer and the LO amplifier come from an Azure and dual power supply. And I've separated those two power supplies for obvious reasons. So it looks good. Now the only thing left to do is to take a look at it on the spectrum analyzer, see if we have our spectrum where we expect it to be, and if it has still a reasonably good quality. And here's the spectrum of our transmitter. It looks like a horror show. Someone's got to call the FCC. There is tones everywhere. Obviously, this is a prototype. I didn't use any filters, and as I pointed out at the very beginning of the video, this is the consequence of that. And it's interesting to see that there are harmonics and signals generated all the way up to near 26.5 gigahertz. That's pretty amazing considering that the components, none of them are rated really more than 10 gigahertz or so. So nonetheless, this is our upper sideband and lower sideband signals centered right around 6.5 gigahertz, which is the tones that we are interested in. So we can actually zoom in a little bit and take a closer look and see if it is what we want. So let's go and set our center frequency to 6.5 gigahertz, which would be right around the frequency I'm interested in looking, and I'm going to change the span and reduce it significantly, and eventually we will see our spectrum. But you just saw how many other, I'm occupying everything under the sun, so obviously you cannot transmit this, and it will never pass mask emission test and so on. But nonetheless, for our experiment, it's good enough, and you can see our main spectrum. So how much has the EVM degraded because of all these components and lack of filtering, and using really just things that are off the shelf, not really optimized very well for each other? Well, we can easily find out by going under mode and going back to the VSA and running it again. Now this time the difference is that the VSA is no longer centered at 500 megahertz. Right now it's centered at 6.5 gigahertz. So indeed we are looking at the upper sideband of our transmitted signal exactly as it should be. And take a look, you can see our SNR has dropped quite a bit by more than 10 dB, and our EVM is 4 times larger. So it is, you can see that the quality of this constellation has degraded. And if you look closely, you can see at the edges and there's some smearing, and that is obviously the effect of the phase noise. So indeed the integrated jitter that we have at 6.5 gigahertz is having some impact and some degradation on the EVM, as to be expected. Now, a few other things to note is that I'm transmitting just under 0 dBm of total power at around 6.5 gigahertz. Obviously, there is a whole bunch of other spectrum, as I said, and those also have power, but the power of interest is in this region. And a few other things to note is that the EVM, as a function of symbol, as you can see, it has a certain degree of periodicity to it. It's not completely white. There's a deterministic aspect to the EVM error, and this is very useful to see. I know where it comes from, but I'm going to leave it to you to discuss in the comment section if you can decipher why we have this deterministic way of the EVM degrading. And this is undesired, of course, because you don't want that. You want a perfectly white EVM so that your channel is basically AWGN. But nonetheless, you can see that very clearly. We can characterize this. So now we have to move on to the receiver, build the receive section, and see if the full chain can finally recover the signal. And finally we have our complete link. This includes the up converter and the down converter between two horn antennas. So I'm going to give you a close look at the receive side, since that's the part we haven't seen yet, and then we'll follow the whole setup from the beginning to the end with the camera and then take a look at the performance. And here is our receive side. As we saw before, we have the EXG synthesizer generating a half rate LO, which goes through our doubler, followed by an amplifier, and then fed into the LO port of the double sideband mixer on the down convert side. The signal comes from an antenna up here and then goes through the LNA, fed to the RF port, and the first IF coming out is then fed to this final IQ demodulator. You haven't seen this board before, so I'm going to talk about it a little bit afterwards. But this demodulator has its own built-in PLL. As a result, it's going to need an external reference, and I'm using a 100 MHz oven-controlled crystal oscillator as the reference of that PLL. So this whole thing is going to do all of our final IQ demodulation. And all the different power supplies are scattered throughout the lab. We have two power supplies here to power the final demodulator, this power supply powering the PA for the LO driver, and finally a laptop over there which runs the GUI that controls the final IQ demodulator. So let's take a look at a block diagram of this so that we can have all the information and fully appreciate what's going on in this setup. And here is the block diagram of the final demodulator. You can see that indeed it has a VCO core in the middle here, and all the required components for a PLL. So there is a PLL enclosed in this section. It also has an LO output and input, which we're ignoring at the moment, but you can see that the output of the VCO drives the divider and a quadrature divider, which generates two IQ signals feeding the two mixers, with the RF input coming over here with the I and the Q outputs. So this is basically the reverse of what this signal hound component does, and this would undo the IQ modulated signal initially originated from the VSG25A. So now that you have a good idea of what this looks like, we can follow the setup from the beginning and the end, and it should all come together. And once again, from the beginning, here's the power supply for our transmitter, and we can follow that, and we can see indeed the transmitter section here as I described before. The output of the PA goes through this horn antenna, and this horn antenna then transmits all the way to this receive horn antenna. The signal from that is fed to the LNA and the receive chain that I just showed you. And here's again the reference for the PLL inside the receiver. We have various power supplies scattered all around the lab, powering different sections, and here's the laptop that controls the software for this receiver. Then the final signal from that is taken over here and passed through a low pass filter before it is given directly to our EXG. And you can already see, in fact, the signal, half of the baseband signal being received over here, and that's because the final receiver is a 0IF receiver, and that's exactly what we would expect. And you can here, of course, also see the EXG generating our half rate LO, and everything looks really good. So the only thing we need to go back is to go ahead and take a look over here and see if that signal indeed matches what it is that we are transmitting from the IQ modulator from the very beginning of the chain. And here's our final spectrum, and you can see indeed that we have half the I and Q signal, so the upper sideband, being displayed here. Now remember what is actually happening. On our transmitter we have our first up converter at 500 MHz, then I'm using a 6 GHz LO that puts our signal at 6.5 GHz, then I'm using a 5.6 GHz down converter on the sliding IF, and that puts our second IF down converter to 900 MHz. Now in order for us to be able to see the I and Q separately, I can't just set the receiver PLL to 900 MHz, which is what I've done over here. That's why you only see half the signal. Now on a different X-series spectrum analyzer, if you have the option with the IQ analysis built on directly onto the front panel, you can actually take I and Q and put them directly onto the spectrum analyzer and have the baseband section process that information for you. But because we don't have that option, that's actually not available on the EXA series, we can only look at either I or Q, and this is in fact the I that I'm looking at. But what if I want to actually demodulate this and take a look at it? Well, I can always change the PLL that's built into the final down converter. Let's shift that PLL by 50 MHz from 900 MHz to 950, and I can go ahead and enter that number over here and run the code, and we should see the baseband signal shift, and there it is. In fact, now we again have our full I section, which is over here, and the Q section be within the analysis window of the spectrum analyzer. So now we can go back under mode and bring the VSA back up, and in fact, let me just make sure. There we go. We can actually bring the VSA back up, and now I can adjust the center frequency and say that the center frequency should be at 50 MHz. There we go, and voila, here is our final received signal, and it actually works. We have a complete super heterodyne with the sliding IF receiver, and the full chain works, and we have our received constellation. Obviously the constellation isn't going to look as nice as it did on the transmitter, and that's to be expected. And in fact we're receiving a very, very small amount of power, and I can change our marker here and center our marker at 50 MHz. And we can see that the total received power from the IF is minus 28 dBm. So it's a very small IF signal, and that's because we don't have a baseband amplifier in this system, and it is normally required in a wireless system like this. But we have an EVM about 5.5%, our SNR is 25 dB, which is, it's okay. I mean, we can still recover with forward error correction this constellation. But it looks good, and if I go ahead and block the beam with my hand, you can see that I'm just right now passing my hand in front of the horn antenna, and you can clearly see the attenuation, and if the noise gets high enough, you can see the SNR of the signal would degrade
as to be expected. Now 6.5 gigahertz still partially passes through my hand, so I can't completely block it, but I can certainly block some of it. So now you have a complete system, and you can appreciate every step of the way what kind of characteristic of each component is contributing to this final constellation, which is ultimately what we are looking for. And there you have it, a whole bunch of different experiments for the EXA signal analyzer. And I know I mentioned that I will take a look at the wideband IF output, but in the interest of time I'm going to leave that for a different video. But the idea is that the wideband IF output can actually have bandwidths over 400 megahertz instantaneous bandwidth, depending on if the right options are installed. And you can take that and then connect it to something like the S-series oscilloscope, which I've reviewed before, and then you can do your digital analysis directly on that, and you're not limited by the 40 megahertz internal analysis bandwidth anymore. And there is a lot of other details that of course I didn't go into, and I'm going to leave a lot of that for some other videos because this video is already over an hour and a half long. And I suggest that you go and take a look at, if one of the particular application interests you, go and look at the data sheet so if you can get some more information about it. And as always, if you like the video, please leave me a comment or rate the video and let me know. And if you happen to purchase these instruments, or if you get useful information from them, let other companies such as Keysight know. I don't get any money from them, I don't get any portion of the sale of these instruments, but it would allow me to have a good relationship with them to be able to bring you videos like this in the future of advanced instruments. So, until next time.